Hello, my name is Rafael Diniz. I'm here to present our article Luminance, Local Luminance Patterns for Point Cloud Quality Assessment. The authors of this paper, it's myself, Rafael Diniz, Mylene Farias, and Pedro Garcia. We are all at the University of Brasilia in Brazil. The summary of my presentation is an introduction first about point cloud quality assessment. Then I go through our proposed method, and later on I'll talk about our experimental setup, the results, and conclusions. So, what are point clouds? Point clouds are a data structure with contained points with 3D position information, plus color information, plus sometimes other attributes like normals, transparency, and so on. Let's go to talk about our topic, point cloud quality assessment. So regarding subjective point cloud quality assessment, there are some experiments in the field. We are using some of these experiments that are carried and are listed here in order we can have some subjective data of point clouds with both reference and degraded versions. So we use these 3 studies that also define some data sets which they carry the study and the scores of the subjects regarding the distorted version and reference version of point clouds. This is Cruz, Torligi, and Alexio. Regarding point cloud objective quality assessment, there are some studies also. There are many metrics, some new metrics that didn't made to this article yet. Was not referenced in this article yet, but 2020 there are some new ones. These are some metrics developed in the past year, in the past 2 years. Most of them are typically based on point-to-point degradation, point-to-plane degradation, and plane-to-plane degradation. That is this first article here by Alexio, and we later use these metrics to compare our proposal with other state-of-the-art proposals, right? Start to talk about our proposal. So this descriptor that we are proposing here, called local luminance patterns, is somewhat an evolution of our prior work that's towards a point cloud quality assessment model using local binary patterns. We evolved a bit the descriptor in order to have a label without much geometric dependence among the neighbors. So our point cloud quality assessment method is divided in 4 steps. The voxelization method or methodology, our novel local luminance pattern operator, which creates a feature map, and then we compute distance between the feature map histograms of the reference versus the test point cloud feature maps, and then we have our quality prediction model based on our regression algorithm. So going ahead. So our voxelization methodology is based on 2 strategies that defines a single voxel size for each point cloud. The difference between our 2 voxelization strategies, I'll talk later. First, it's important to say that point clouds are composed typically, well, when you say point clouds, they're composed by points, and points themselves don't have any volume size. So how to represent these points? So one solution is to voxelize these points, right? In order they have some size, typically cube shape. So going back to our strategies, we have our S1 strategy, where we calculate for each point cloud, independent of the content, the voxel size separately. So we get the reference and the test point clouds, and they have a different voxel size. For our strategy S2, the test point clouds and the reference point clouds have the same voxel size, and this voxel size is defined by a formula that it's in the next slide, only applied to the point cloud with less points of a same set of reference and test point clouds of same content. So let's go ahead. So this is how we calculate the voxel size, which is the cube of the edge size. That is basically the distance, the average distance of the nearest neighbor of each point divided, multiplied, that's the average nearest neighbor multiplied by a k constant, and this multiplier k, we chose one based on our experiments, and one different k for each voxelization strategy we chose. So we go ahead now. This is how our descriptor works. So first we convert the points RGB to luminance only, just to grayscale, using the BT709 recommendation. In our case here, we get the 8 nearest neighbors for each point, and we extract a label based on the colors of this neighborhood. So we define, in our case in this paper, we define 16 beans, and then we set the bit in there if there is a corresponding RGB range of that bean, just like here. So for example, the first bean colors luminance between 0 and 16. I would set bit 0 of this label. If there is a neighbor with color between 16 and 32, I set bit 1. If there are two colors in the same range, I just keep the bit set of this label. So this is how the LLC creates a label for each point. And then we get this feature map, extract histograms from it, the frequency of each label, and then we carry the calculation of a distance between reference and test histograms, and then we have a score from it. And later on, we need a function to fit our data to better match the subjective scores. So we applied we applied a regression function in order to fit our data to be more correlated to the ground truth. So we tested 12 regression models, the random forest regressor, extra trees regressor, gradient boosting regressor, Bayesian ridge, ARD regression, Lars elastic net, ElasticNet, CV, Lasso, Ransack regressor, K-neighbors regressor, MLP regressor, and the logistic function. We chose the logistic function. In our article there are some results of the test we carry on, which indeed matches the literature, which really puts the subjective data scores of this kind of experiment, fits well the logistic function. So we calculated to choose the logistic function, we calculated the PCC, SROCC, RMSE of different regressors, and we chose the logistic function, and second best, not very far behind, are the random forest regressor and the MLP regressor. So now going to our experimental setup. So I already mentioned 3 data sets and associated subjective scores we used for this comparison of our descriptor, of our proposal. Here are the names of the articles where we got the subjective scores and the data sets. We compared our proposal with this classic already point cloud quality assessment metrics, and well, these are the results. We calculated the PCC, SROCC, RMSE of our metric and the others that I mentioned. Here, to simplify the exhibition, I just put the second best or best performance metrics compared to ours. And well, for the first data set, we have the best PCC and lowest RMSE, which are the best among all the metrics we tested, and close SROCC value. For the second metric, the only one we didn't perform better. With the first voxelization strategy we were not very well. The metric did not perform good, but with the second voxelization strategy it performed better, being like almost second best. And for the third data set we were again the best one, with point to plane MSE close to our score, a bit ahead in the SROCC. So, but in the average, we have the best performing metric in relation with the metrics we tested. It's the more stable, let's say like this, among 3 data sets, especially if we combine the both strategies. So the results are that we have a strong a metric that shows strong results, and it's a promising performance, and we hope to study and understand better why the different voxelization strategies perform different in different data sets, and maybe we want to develop some strategy that works better in all data sets in future works. So I think that's our presentation. Thank you very much. I hope to talk to you in the virtual pitch about this work. Thank you very much. Bye bye.